All right, so kind of things to go through before we jump into material here today. We will finish module 12 today. So I've actually already got that. Oh, I'm on the wrong section. Hold on. I've already got that module. There we go. 12 quiz ready to go. As soon as we're done today, I'll kind of publish that. We'll have today's participation quiz. Those will both be due at the end of the day this Thursday. So tomorrow, in fact, we'll kind of start to introduce the idea, I think, at the end of class of module 13. We'll really dive into it tomorrow. So that module 13 reading is due before we start class tomorrow. We'll have the 2 participation quizzes for Tuesday and Wednesday for module 13, as well as that module 13 quiz, which will be posted Wednesday. All of those will be due at the end of the day Thursday. Thursday's class period will be doing review, mainly going through these practice problems, some additional problems maybe I bring in that I think might be wink, wink helpful for the final. And then we'll have that final exam, which will be on Friday. So kind of similar to the last one, you'll need that lockdown browser. It'll be available a little bit longer. So I think I'm going to have it set to be, instead of 11:15 to 3:15, 10:30 to 3:30. So a little bit wider of a window on Friday. And you'll have an hour and 30 minutes instead of an hour and 15, because there will be 30 questions. So it'll give you a little bit more time since there's a few more questions on there. So that'll be due Friday. We'll talk more about that as the week progresses, but kind of getting that out there now, making sure that during that time frame, once again, it's the same as the last one, just extended a little bit. So 10:30 to 3:30 there. Making sure you have access to a computer or device to be able to take that exam with that lockdown browser already kind of downloaded and ready to go. Other than that, after tomorrow, after we have that last module reading, I'll start to update Canvas so that it will reflect your lowest dropped. We went through that hypothetical grade tool that you can enter your grades in, where it will kind of drop your lowest and show you what your score would be in each of these different categories under the assignments tab on Canvas. As the due dates pass, I'll kind of update Canvas so that it drops your lowest module reading, drops your lowest 2 quizzes, etc. Okay. So last week we're gearing up towards the end here. So if there isn't any other questions, we'll kind of finish up module 12 here. Any logistical questions? Okay. So module 12, we left off kind of looking at more of these market-based examples, firm setting quantity and price. We said this prisoner's dilemma would push them closer to that perfectly competitive outcome. So I'm going to have a slightly different example. I'll try to give a lot of market-based examples. This is a business class, but we can see game theory applied to a lot of other areas as well. So political science is another area that uses game theory. So here we'll just kind of build a simple example. 2 people, right? 2 different decisions, and then payoffs of those decisions. So let's say I've got 2 candidates, Republican and Democrat. I'm thinking about, they have the decision to make at the same time, or am I going to run negative attack ads against my opponent, and vice versa. If one of them runs negative ads, so if the Republican runs negative ads, but the Democrat doesn't, the Republican will gain 1,000 votes. 3,000 votes will be lost from the Democrat, which means there'll be 2,000 people that abstain or don't vote. Right? Same kind of idea. If the Democrat runs negative ads, the Republican doesn't, the Republican loses 3,000 votes, the Democrat gains 1,000, 2,000 people don't vote. And then if we have both of them run these negative ads, we'll lose 3,000 from each, but they'll each gain an additional 1,000, so they would be losing 2,000. So I've kind of got the solution to this game, but let's kind of walk through just to kind of a refresher of how we solve these games. Okay. So I can run these negative attack ads, or I cannot run. Let me make sure. Who did I have on the side here? This was the Democrat. And then we can run or not run negative ads. If I'm the Republican, we said sometimes we'll kind of use these normal form game matrices where the lower left is representing the person on the left, or person kind of 1 here. So if they both ran negative ads, oh, and I think I have the reverse of the slides, but that's okay. Yep, I do, but that's fine. So if they both choose not to, nothing changes, right? No votes are gained, no votes are lost. If they both run negative ads, they'll convince 1,000 people to switch, but then there will be 2,000 2,000 people who just stop voting. Well, if there's 1,000 that switch both ways, offsets, they just lose 2,000 votes each. If I don't run the negative ads, but the opponent does, they'll gain 1,000. I'll lose 3,000. If I run negative ads, they don't, I'll gain 1,000. They'll lose 3,000. So just a reminder, how do we solve these normal form games? So we're going to go through and make the best response for each individual to the other person's best response. So if the Republican candidate is running these negative ads, what should the Democrat do? Well, losing 2,000 votes is better than losing 3,000. So they would combat that with also running negative ads. If the Republican candidate does not run negative ads, well, if I do, I'll gain 1,000. If I don't, nothing changes. Well, gaining 1,000 votes if I'm trying to win an election is better, right? So we kind of have the Democrats' best responses to both of the strategy choices of the Republican is always to run these negative ads, leading us to a dominant strategy for that Democrat. What if instead we look at the Republican's best response? So if the Democrat runs these negative ads, if the Republican does as well, they lose 2,000. If they don't, they lose 3,000. Losing 2,000 votes is better than losing 3,000. Here, what if the Democrat doesn't run these ads? Well, if the Republican does, they gain 1,000 votes. If they don't, 0. So the Republican also has this dominant strategy to run these negative ads. We said the most non-technical way of identifying these Nash equilibrium is where we have two circles in the same box. Or really, what does that represent? We are both best responding to what the other person's best response is. Okay. So here, we end up in this scenario where they're both losing 2,000 votes, which you could argue this isn't a prisoner's dilemma in the sense that, well, the kind of difference in the votes would be the same here, right? But as a candidate, you always want to have more people voting for you. You want to have more of your public or constituency behind you. And so you really losing no votes is better than losing 2,000, right? And so because we end up with this Nash equilibrium, both candidates could be better off if they could agree to a different combination of strategies, in this case, to both not run these negative ads. Not only does this have negative implications for the players involved in this game, this is where we also start to see these games, sometimes there's losses to people outside of this game as well. So this would create a negative externality for society. We could then go through our negative externality models and say, okay, not only do we end up at a worse outcome for the two individuals in this game, we end up in a non-optimal or a worse outcome for society as well, which is just that we're having more people kind of disenfranchised and don't want to vote in these elections. Okay. So slightly different example than kind of what we were looking at last class, but we would go through and solve it the same way. As long as we have simultaneous decisions, we're making the decision at the same time, whether or not we run these ads or not, we could end up with identifying the Nash equilibrium. And here we have an example of a prisoner's dilemma. Okay. So, we said it's not only bad for the people involved, it's also bad for society. Okay. All right. So one thing that we didn't really get to last class is even though we have these Nash equilibrium where whether or not it's two politicians deciding whether or not to run negative ads, whether or not it's companies setting high, low prices, if you repeat the game, sometimes we can have different outcomes, okay? So we'll kind of talk about some strategies that could lead to cooperation. So one of them that we'll talk about is this tit for tat strategy, which is if the other person breaks an agreement, I don't trust them for any other round. So let's say we have this game. We'll start out assuming one where we've got, it's played 10 times, right? And we're thinking about two firms setting prices. If one firm breaks the agreement to set a high price, so let's say they decide, okay, I'm going to undercut the other person's price. Everyone will buy from me. I'm going to make a low price. The other firm won't trust them for all the subsequent 9 rounds. So if we're playing this game 10 times, whether this is setting prices 10 days in a row or 10 months in a row, I always think about this like gas stations, right? If they're, let's say they're setting prices at the same time in the morning, 9 o'clock, that switches over. If they both agree to set a high price, that's good. We keep making that decision for the next 10 days. As soon as the other person lowers the price, I don't trust them for the remaining rounds. Okay. So we'll kind of think about how we could model this and show why, if we play this game multiple times, why we could end up with a different equilibrium than if we just played it one time. So if we think about here, let's say we've got two firms. So firm 2 firm one. And we're not being super specific with exactly what the price is, but a high or a low price. We'll kind of assume this high price in any one time period. If we both set a high price, we're kind of acting like a monopoly. We could split monopoly profits, right? So let's say there's 20 million, I'll just use, instead of writing the millions in here, just write 10 to kind of represent this. However, if we play this game for 10 times, if we agree to work with each other every single time, we're both going to be earning what? 10 times 10 or 100 million in profits. Now, if I break, let's think about that first time period. If I break the agreement as firm one instead of low price, everybody's going to buy from me. Maybe I could make 20 million. The other firm is going to lose 5. Now, for every round past that, I don't trust the other firm anymore. Firm 2 will no longer trust firm 1, and they'll automatically go to setting that lower competitive price. So in every time period where we both set a low price, our profits are 0. We're at this perfectly competitive price. And in practice, it might take time to kind of trickle down to that. But just for the sake of kind of seeing where it'll go, we can depict it just using a high and low price value. And then if I set a high price and the other firm undercuts the price, well, they might be able to earn 20 million in that first time period, but I'm never going to trust them again. So I lose money in the first time period, but after that, we both go to setting low prices, and that kind of continues until the remaining 10 rounds are over. So if by agreeing to work together, we can continue to work together for subsequent time periods, maybe that changes the payoffs. So if we're thinking about what's the firm's decision in that first round, okay? Well, if firm 2 sets a high price, what should firm 1 do? Well, if I go for the short run gains, I wouldn't be getting all of those future profits where we're agreeing to work with each other. So notice here, it's actually optimal for me to set a high price. What if firm 2 sets a low price? Well, if I if I set that high price, right? Well, it doesn't make any sense. Everyone's going to buy from them. So I should actually want to choose down here. Right? And then if firm 1 sets a high price, what should firm 2 do? Well, if I choose a high price, they'll keep on working with me to, agreeing to charge a high price or monopoly profits and split them. If instead they set a low price, what should I do? Always kind of switch over to low. So notice we have multiple equilibrium here, right? I either end up in this scenario where both firms trust each other and continually keep setting these higher prices, or both firms end up as soon as one of those firms is setting a low price, we're both setting low prices. We don't really know. Much like the answer in economics can sometimes be, the equilibrium of this game would be indeterminate. We have multiple equilibriums. So we said last class that can happen sometimes. Okay. Now, even though we have multiple equilibrium here, what we'll end up seeing is firms often, even if we play this game over and over, there will come a point where this no longer will end up being an equilibrium. So let's think about why. So if we're playing this game 10 times in a row, let's think about what happens once those two firms get to the very last time. So they've played it 9 times, they've trusted each other. In the very last round, when they're setting prices, now if we think about what are the payoffs that exist, well, if this is the last round we play the game, the only reason profits were this high is because we were thinking about if I agree to set a high price and I do, they'll trust me for the next 9 rounds. Well, now there's no more rounds left. So if we agree now, well, we're only earning 10 million, right? 10 million each year, 10 times we play the game. That's how we came up with 100. However, if I break the agreement in the last round and I set a low price, everybody buys from me. Same idea over here. If I set the low price as firm 2, everybody buys from me. The other firm, they're staying open. They just lose. They don't make any revenues, but they lose whatever their costs were. And then if we both set a low price, we're at that perfectly competitive, kind of splitting, we have 0 profits. So how would we solve this game? So to kind of color code this here, got firm 2, firm 1. If firm 2 is choosing to set a high price, in that last time period, what should firm 1 do? Set a low price. Firm 2 is setting a low price. What should firm 1 do? Set a low price. If firm 1 is setting a high price, what should firm 2 do? 20 is greater than 10. If firm 1 sets a low price, what should firm 2 do? 0 is greater than -5. Notice in the last time that game is played, that last time period, it actually goes back to where we only have one Nash equilibrium, which is in that last time, both people break the agreement. Okay? Now, sorry, my lights turned off. Now, this is where I wouldn't, this is, as far as I push you is to kind of give you the payoffs and have you solve a game like this. In practice, this is kind of interesting because if this is the incentive that exists in the last final 10th round, well, notice if I know that the other person, if I know this is the equilibrium in the 10th round and they're going to break the agreement, what does that do to these profit values? Well, it actually would change them to 90. But then if we go up to the 9th time period, if I know the other person is going to break it in the next round, well, then I want to try to be the person that breaks it in this round. So then this only becomes 80. And then if I know that they have the incentive to break it in the 9th round, I want to break it in the 8th, and then 7th, and the 6th. And that logic would apply to basically, we see that as long as there's a finite time, like the number of times that we're repeating this game, there's always the incentive to be the firm that breaks that agreement first, and we end up with this multiple equilibrium example doesn't actually hold. Now, if it's an infinitely repeated game, we never know when that last time period is going to be played. Well, then we can still end up with a game like this, right? So it's kind of good news is that, firms usually generally make decisions as though they're going to remain in business. So there is no like end date in terms of how many times we're going to be playing this price setting game. Okay. So I don't know, just a kind of a short example with our basic kind of 2x2 matrices where we can see we can change the equilibrium sometimes if this game is repeated, especially if it's repeated indefinitely. Okay. Let me get this out of here. All right, so we did our research and development example last class. One that we didn't quite work through that I think is worthwhile is what if I had multiple choices, and I won't give you a 3x3 matrix on the exam, but I think it's worth kind of thinking through how we would solve these and to see that, in practice, obviously, companies cannot just set a high or low price. They can set the price at 100, 99, 98, etc. Right? So this game will point out two things. So the first is we can solve these even if we don't have just a 2x2 matrix. Let's say the players have three choices. So if you haven't heard of, know the game, I think it's pretty popular in America with young kids. You play rock, paper, scissors. You both get to choose either rock, paper, or scissors. Rock beats scissors, paper beats rock. Scissors beats paper. Okay, so you both kind of use your hand to choose one of these options at the same time. And the goal is you want to have the winning kind of combination. If you both throw the same thing, nobody wins, nobody loses. So zeros here, no one wins, no one loses. 1, if they throw rock and I throw paper, I win, payoff of 1. They lose, payoff of -1. Okay. So how would we solve a normal form game like this? Okay. So we both throw the same thing, zeros. Right? If player 1, and this is player 2, player 1 throws rock, player 2 would win, right? Because you can kind of imagine player 1, if they throw rock, beats the person that played scissors. This person would beat them. If they play paper, this person would paper beats rock. Paper beats rock. Rock beats scissors. Scissors beats paper. Nope. Oh, paper beats rock. This would be -1. And this would be -1. And then rock beats scissors. So this is -1. Sorry about that. And then rock beats this. So, in fact, I'm recording this. Should be. Yeah, there we go. All right. So, if we had kind of this game, what would our kind of equilibrium be? There is no equilibrium, right? It's just kind of a guessing game here. If we go through and make like each individual's optimal decision, there is no equilibrium. Okay. Let's see where we're at. So we don't have kind of two circles in the same box here. We don't end up with an equilibrium. It's basically a guessing game. Okay. Where am I? Any questions before we keep moving? Got people in here. Okay. So I confused myself. What did I skip? We did this last class. So I think we were right here. Oh, now I'm confusing myself. What did we just go through? We just did paper, scissors game. Why am I blanking on where we were just were? Here we go. Sorry. Let me say, I know we were somewhere. So, all right, my bad. So if we go through this, we could solve this by kind of thinking about where is each person going to maximize their profits. And so if I think about here, if player 2 throws rock for player 1, what's best? To throw paper. 1 is the highest here. What's the highest over here? 1. If person 1 throws rock, what should player 2 do? Throw paper. If they throw paper, they should throw scissors. If they play scissors, they should play rock. Notice we don't have two circles in the same box. That's the least technical way of saying we don't have an equilibrium. Okay, so we can have these examples. Excuse me. There we go. Sorry. Where the best responses of both individuals leads to there is no Nash equilibrium. Right? If I'm playing a game of rock, paper, scissors with someone, if I know what they're going to do, I can always change my decision to beat them. Okay, so it's basically a guessing game. So instead, if we're making these games, these decisions not simultaneously, but sequentially, some of the outcomes of these games will change. Okay, so the way that we're going to solve these sequential games when people make decisions at different times is using something called backward induction. We'll figure out the best response of the person going second, and then knowing that, what would be the best response of person 1B. So let's say I kind of set this up, kind of a goofy example maybe, but if you ever seen the cartoon of Charlie Brown, it's this running joke in the comics where Charlie Brown runs to try to kick a football, and at the last second, Lucy pulls the football away. Now, in this example, Charlie Brown is deciding whether or not to reject, not run towards the ball and kick it, or accept the ball and kick it, accept the offer and try to kick the ball. Lucy then has a decision to make. Do I pull the ball away at the last second and Charlie falls down and I'm amused? Or do I let him kick the football? So we'll solve Lucy's decision first. So if Charlie Brown accepts the offer, if she pulls the ball away at the last second, she is amused. She doesn't care about his payoffs. She only cares about hers. So she finds this funny. If she lets him kick it, she's not. So what is it optimal for her to do? She's going to pull the ball away at the last second. Well, knowing that, if Charlie Brown is making the decision, he knows that if he tries to go kick this ball, she's always going to pull it away. That's always what's in the incentives would make her do. So I know that if I accept the offer, she's always going to pull the football away and I'm always going to fall down. So what's better, me falling down by accepting the offer or just rejecting it and nothing happens? It should be that he always rejects the offer, which is why in the comic, the running joke is like he runs and tries to kick the football, even though he knows that's always resulting in a lower payoff than if he just decided not to accept that offer. Okay. So we'll work through some different extensive form game models. So I'll kind of draw some of these out for us here. So I'm going to be copying a little bit kind of from the slides over. So instead of this Charlie Brown example, let's think through a different one where it might be a little bit, I won't say trickier, but just, you know, a little bit more practical as opposed to like a, I don't know, comic book example. So let's say we've got, I've got an entrance exit example here. I'm going to actually show you a slightly different example first. So let's think about, we go back and we said earlier with our normal form game, if we were setting simultaneous prices, we had this prisoner's dilemma example where it resulted in potentially both of them in that very last time period, both breaking the agreement and setting a low price, right? Trying to kind of be the one that had the lower price. So let's think about instead, if we're making sequential decisions. So let's say firm one can set either a high or a low price. And then in response to that, firm two makes their choice. Okay. So I'm just going to use H and L here just to sake of kind of saving some space. So if they both set a high price, right, that's kind of acting together like they're a monopolist. This is the example where, okay, maybe we can split current monopoly profits. Now, if I set the firm wants the high price, and as firm two, I set a low price, maybe everybody buys from me. So we're writing firm one's payoffs first and firm two's payoffs second. So if firm two sets the low price, they earn all 20 million. The firm setting a high price, no one buys from them. They lose out on whatever their costs are. Then over here, if firm one sets a low price, but firm two sets the high price, firm one, everyone buys from them. Firm two, they're going to lose money. If they both set a low price, maybe they're at that perfectly competitive point. So how would we solve a game like this? We're going to use backward induction. We're first going to figure out what is it optimal for firm two to do. If firm one sets a low price, what should firm two do? Also set a low price. If firm one sets a high price, what should firm two do? Always set this lower price. Okay. So knowing that, if I'm making the decision first, so try to color code this here. What should firm one do? Well, if I set a low price, I know the other firm will always in response set a low price as well. Excuse me. So I ultimately know like this isn't even going to be an outcome. So if I was solving these games, what I typically do is like, okay, I know firm two isn't going to choose to go high. They're going to choose a low price in both scenarios. So this will never even be an outcome. If I set a high price, what will firm two do? Always set a low price. So I know this isn't a possible outcome. So if I'm going to set a high or a low price, and I know if I set a high price, firm one will set a low price, I'll lose 5 million. If I set a low price, they'll also set a low price. 0 is better than losing money. So we actually end up with just the threat, if it's a sequential game, the threat that the other firm, you know, knowing their best response, it would still also push us to this point where we actually both set a low price, right? We're worse off than if we could agree to work together. So we still kind of have, we usually don't refer to it as this as much, but there's still like a prisoner's dilemma, even if the game is sequential, because we still get driven to this Nash equilibrium where we both set a low price. And we could be better off if we agreed to coordinate our actions to do something different, which would be to both set a high price. Okay. Any questions on this idea so far of backward induction? And this is starting to kind of look at extensive form games here. Okay. Oh, what do I want to do next here? So we've already worked through this. Where are we at on time? Okay. So the next thing we'll want to do, where am I blanking on? We started at 2, right? Yeah. So what's the next thing we want to do here? We just went through Charlie went through sequential. Okay, so this one is going to be another one, and I've got it kind of in the slides here. I'll kind of build it out and show you how we would kind of go about solving this game. So this is the one that we're going to try to mimic, but I'm going to write it out just to kind of give you a little bit more insight in thinking about kind of solving these sequential games. Okay, so let's say instead of price setting, right, we think about a game, excuse me, where, let me make sure you guys are seeing this. I've got an existing firm, and so we'll call this like, I think in the slides I said this is like a monopoly, but it's just to make it a little bit more clear. It's the existing firm, and they can set the monopoly price, or they can set a price closer to, if not the same as, that perfectly competitive price. Okay. Here we've got the entering firm's decision, right? So they can either decide to enter this market or exit. So if we kind of start out, we've got this monopolist, they're going to set the price, and then in response to that, potential firms that were thinking of entering or exiting this market will choose to either exit or exit. We'll keep it at kind of a simple, there's only one firm entering or exiting to start out with. So if they set the monopoly price and another firm enters that market, right? Whatever firm, what do I want here? So if they set that monopoly higher price, then the firm that enters, right, their profits, we can kind of think about this as like firm 2. So I'll just use 2 to kind of notate this. And then this is firm 1. The profits of firm 2, they enter that market, they can undercut that price. Everybody buys from them. They're going to have positive profits, while the existing firm that was setting a higher price, right, is going to be earning negative profits. Okay. Now, if they set the high price and the other firm stays out, well, then they enjoy monopoly profits because there's no one else to buy from. And the firm that stayed out, they're just as well off as if they, as they were before. Their profits just remain at 0. They're not in the market. Okay. Now, if we have the flip where they set a competitive price, if this other firm enters, if this is a market where there's only enough demand to really support profits of one firm, and even at that competitive price, 2 firms, it can't support this market, or sorry, the market can't support 2 firms. If a second firm enters at the perfectly competitive price, profits of both firms would be 0. And then if that other firm, I put exit here, sorry. I'm talking and writing and not thinking about it. They weren't in the market yet, so they weren't exiting, right? They were staying out. I guess you can kind of think of it as exit, but they were just staying out of the market. If I set the perfectly competitive price and the other firm stays out, well, if it's a perfectly competitive price, then I'm earning 0 profits, and the firm that stayed out, they have 0 profits. So if I use backward induction, if the existing firm sets a competitive price, what will the firm thinking about entering do? Well, if they enter the market, negative profits. If they stay out, 0. That lower competitive price like scared them out of joining that market. So we know that they would never choose to do this. So firm 1 can kind of think about this isn't an option anymore. If I set a perfectly competitive price, I know this is the equilibrium or the outcome that we'll get to, the payoff we'll get to. Now, if the existing firm is setting a higher monopoly price, they know that the firm thinking about entering, if they enter, right, they could be earning positive profits. If they stay out, profits are 0. So they know that firm would choose to enter and kind of undercut my price. So I know this won't be a possible outcome. So if I'm then thinking about the existing firm, they look at these payoffs. One thing we're assuming in these models is that both firms can kind of know the payoffs of the other firm. And so they know that if I set a perfectly competitive price, the firm thinking about entering will not. and I'll be earning zero profits. If I set the monopoly price, I know that the other firm will enter, driving my profits to negative. What would be better? Profits of zero as opposed to negative profits. So what do we end up with? We're going to have this Nash equilibrium, or this extensive form Nash equilibrium, where the existing firm will set a more competitive price that encourages or leads to the firm thinking about entering to stay out. We still only have one firm. Profits of these two firms are zero, but they set that price closer to, if not exactly equal to, that perfectly competitive price. So kind of a good news for consumers there is that even the threat of a firm entering can push that existing firm to setting a more competitive price. Okay. Any questions there before we keep on moving? Okay. All right. So, what's the one I have? We'll do this one first, and then we'll kind of come back. So let's say we go back to, just to kind of give an example. Let's say I have this rock, paper, scissors game. Okay. We can use the same type of logic if instead of throwing or choosing rock, paper, scissors at the same time, if we make that decision sequentially, well, if you know the game, you know that that would make it not very interesting. Because if I know what the other person is going to do, I can always beat them. So we can actually model that, though, and see that that's the case. So notice if person one has to choose rock, paper, or scissors first, and then in response to whatever they choose, person two gets to make their decision. So if I play rock, and the other person plays rock, nobody wins. If they throw paper, I lose as person one, they win. So -1 to person one, +1 to person two, they won. If they throw scissors, well, they would lose. So I would win, they would lose. What's their best response? Player two, well, that would be to play paper. And then if I throw paper, what's their best response? To play what would beat that, which is scissors. And if I play scissors, what's their best response? To play rock. So I first identify the person going second, their best response to each of my possible responses. Once I do that, I could almost like cross out every single one of these where I know that they aren't going to choose that. So when I'm really comparing from person one, what should I choose to do? I'd be comparing the outcome or the payoff of wherever person two's best response is. So -1, I'll notice here, I'm indifferent, right? Between any of those payoffs, I know whatever I throw, the other person will always just choose whatever beats me. So here we have an example where we don't know what the outcome is going to be because person one, they don't care. They're going to lose this game no matter what. So we don't know what the Nash equilibrium is going to be. Kind of once again, indeterminate here of which of the outcomes we're going to see, but we know it's going to be an outcome, one of these three, where person two wins. So we started out originally, we had a simultaneous game. We said there was no equilibrium, right? There's no two circles in the same box here. So we don't, it's ultimately a crapshoot. There is no equilibrium here. If we make it sequential, now we end up with multiple equilibrium as opposed to none. And all those equilibrium will be that person one loses, person two wins. Okay. So just kind of an example where if you change a game from sequential to simultaneous or vice versa, in this case, we were going from a simultaneous decision to sequential, it dramatically changes what the equilibrium is. In fact, here going from no equilibrium to multiple equilibrium. Okay. All right. Any questions? Oops, I didn't mean to do that on that before we keep moving here. So I'll come back to this sharing example at the end. But I don't want to do that. What I do want to go through is participation quiz for today. Okay, so we'll take a look at it here. So what if I had a game where, once again, we're kind of in this extensive form game mode. So last class, we talked about examples where firms would invest in the research and development or not. Okay, well, we were doing that as though it was a simultaneous decision. Let's build this out as though it's a sequential decision game. So once again, I'm going to write this out so that we can kind of solve this. And I don't have to just like circle things on the screen. I think it's maybe a little bit more clear if I write this out and kind of show you how I would solve this if I had like the physical ability to like cover things up to kind of give you a little bit more insight. So invest, do not invest. So if both these firms invest money into research and development, this is the idea that, okay, we're coming up with these new products. We're generating a lot of money, both of us, and we both had to spend money, but now we've got like each came up with a new product. We can gain a lot there. If we both failed to invest, maybe we were still both earning profits in this market, but not near as high. And then if I'm the firm that invests and the other firm doesn't, well, I've spent a lot of money. They mimic my product. I'm kind of splitting the money made off this new product with them. And so maybe I actually lose money because I had to spend all this money to come up with a new product. They're making a bunch because their costs are essentially zero in terms of their research and development costs, but they're now able to mimic whatever I came up with. And then the flip side would be true if firm one doesn't invest, but firm two does. Firm one can make a bunch of money, and firm one is going to end up losing out. Okay. So if I just wrote down exactly what that game was, we would solve this using backward induction. So the way that we do that is think about if firm one chooses not to invest, and I just put I here for invests. Well, if firm two chooses to also invest, if firm one doesn't invest and firm two chooses to invest, they would lose 20 million. If they don't invest, they keep that same positive 10. This is kind of the better option. So we know they won't choose to do this. If firm one chooses to invest, what should firm two do? Well, if they invest as well, they get 50. If they don't, they get 60. So we know they will choose not to invest. So knowing this, firm one says, if I choose to invest, I know firm two will always choose an option that leads to me to losing 20 million. But if I don't invest, I know firm two will always choose an option that leads to me making 10. 10 is better than negative 20. So we end up with this Nash equilibrium when this game is played sequentially, where both firms would choose not to invest. Okay. Excuse me. Any questions on that idea before we keep moving? I'm going to complicate this a little bit. Okay. So what if instead, and this will be kind of similar to when we were looking at these in the last class, we had, even if this was a simultaneous decision game, we said patents could change the outcome. So without patents, when they could just mimic each other, right? It was always better not to be the one investing because I could just steal from the other person without having any additional costs. Okay. If I think about instead a game, so this is invest, do not invest, invest, do not. Let's say I've got a patent so that if I'm the one, so first of all, if we both don't invest, no new product, we're both earning 10 million. Okay. If instead we've got it such that, what do I want here? I forget what it was. So let's say, if I don't invest and the other person does, they come up with this new product. So a lot more people are going to like go to buying their good. Now they had higher costs, but they're going to get a lot larger portion of demand. So maybe I end up with something like, I don't know, I could even say maybe firm one is still making, oh, that's not firm one, sorry. Firm one is still making some money, but firm two, the one that invested, is now maybe making, I don't know, 30 million. And then over here, if firm one invests and I don't, right, as firm two isn't going to make near as much as firm one. Okay. And then if we both invest, we're still kind of splitting demand, but we've come up with these new products. We've increased our costs, but we've got like these better products for society overall. And so maybe we're selling more if we can kind of protect these. Now, those payoffs aren't near as high as they were before, right? Because now I can't sell my product and the other person's. I can only sell mine. But we'll notice in a game like this, if we were to solve this one, well, what is it optimal for firm two to do? Now, if the other firm doesn't invest, they should invest, right? If the other firm does invest, what should firm two do? They should also invest. Knowing that, right? If firm one chooses to invest, they know that this will never be an option and this will never be an option over here. So if they invest, they know they're going to get 20. If they don't invest, they know they're going to get 5. So by creating kind of protection for these firms with these patents, we've actually resulted in a new equilibrium, which is that both firms choose to invest. I circled firm two. Sorry, I was meant to circle the word invest and I hadn't either. So, right, we've changed the equilibrium from not investing when there was no patents to investing if we had them. And I'm not going to expect you to know like how the payoffs would change if we had patents versus not, but I would give you the depiction of what the payoffs look like and have you solve these extensive form game models. Okay. So in the original problem, we had this Nash equilibrium where neither company is going to invest. And then if we had patent protections, that's the one I drew in there where you could see it could switch it to they both start to invest. Okay. Is that clear? I know it kind of bounced back between those two. Any questions there before we keep moving? Keep an eye on the chat. Okay. Oh, which one do I want to do first here? Let's go back to the slides before we do question 2 and think about what the equilibrium would be in this interesting kind of little sharing example. So let's say, because I want to stick with extensive form games, and the one that I'm going to kind of look at, we're going back to looking at like a simultaneous decision game. So we'll kind of end with that instead. So I'm still looking at these extensive form games. Let's say I had this set up, and they've run these in economic experiments labs where they actually have gotten money to do this. And they will give someone $100 and say, okay, look, you can divide this up into $1 increments and offer your friend or this other person a certain amount of money. So you can take this 100, you can offer them $1, keep 99, offer them 10, keep 90, etc. If they accept your offer, you both get whatever the offer was. So if you offer them $10, they accept it, they get 10, you get 90. If they reject it, you both get nothing. Okay. So we can actually model this as kind of a extensive form game because it's simultaneous decisions. One person makes the offer, and then the next person is kind of choosing whether or not to accept. Okay. So firm, let's do, these aren't firms. These are person one, right? So let's kind of start to think about, I can make different offers to this person. And really there's a bunch, but we'll just start out with 3. So I can offer them nothing, so 0 of the $100, 1, or I can offer them 2. Okay. So in all of those scenarios, person 2 then can either accept or reject that offer. Okay. And once again, I could offer them 3, 4, 5, etc. But we'll look at this and say that the same logic would apply. We can actually figure out the outcome just by looking at these 3 values for now. So if they reject any offer, both of us get nothing. If I offered them 0 and they accept it, I get to keep 100, they get 0. If I offer them 1 and they accept it, I keep 99, they get 1. If I offer them 2 and accept it, I get 98, they get $2. So if we use backward induction here, if I offer them 2, what should person 1 do? Well, 2 is better than 0, so we would say that they accept this offer. Same idea here. 1 is better than 0, so they'll accept it. 0 is the same as 0. So here we actually don't know. They would say they're indifferent between accepting and rejecting this offer. So technically, what the Nash equilibrium of this game would be is, well, I know that here I would probably want to do like an expected value. Well, if I don't know which of these they're going to choose, half the time they could accept or reject because they're indifferent. Well, then I know the expected value there for person 1 would be, what, 50? Whereas here I know they're always going to accept, so it's 99. So we end up seeing that kind of equilibrium for this game. And I wouldn't give you one where it's indifferent. I would kind of give you one where it's clear and you can identify one specific kind of value being higher. So I would give you something like, I don't know, 0 and -1 or something like that. So or sorry, -1 and 0 or something like that. But for now, so I know that they're always going to kind of choose to offer just slightly above. But then if I look at this, okay, I know that they're always better, like they're always willing to accept the offer. So if they're always willing to accept the offer as person two, what do I want to do? I want to offer them as little as possible while still knowing they'll accept the offer. So for person two, or sorry, I always know what person two is going to do. So for person one, where is my payoff higher? Well, if I offer them $1 instead of $2, right? I actually know that that's where I'd be better off. So we know that this person has the incentive to offer as low as amount as possible. And as long as that person accepting or rejecting the offer, as long as if they reject it, they get nothing, they're always going to accept even the smallest amount that I offer them. And, you can kind of almost model this with like people in the government, right? And we're always willing to take, even if it's a small kind of tax break or something, we're always going to take that over nothing. Okay. So in this sharing example, what we end up with is this equilibrium where person one will offer the smallest increment to guarantee that's the last place where this person would accept it. But if I know they're going to accept 1, 2, 3, 4, 5, 6, if I know they'll accept anything that's above 0, I want to choose the lowest amount possible because that would generate the highest kind of possible split of that $100 for me. Okay. Any questions on this? I'm going to complicate it a little bit, but try to make this kind of a more real world example for us. Okay. All right. So they've run this in experimental economics labs. And what they find is that actually, if this same scenario is given, most people reject offers of like $1 and $2. Okay? So think about, put yourself in those shoes. If you know this person has $100 and they're making you one offer and they say, I'll give you $1 of that 100. I know that you'd be better off, so you'll accept it. You feel kind of done wrong by that person, right? So what we actually, the way that we kind of see this modeled is it's not just, so even though this is the amount of money they're offering the other person, so this is the decisions of person one, when person two is thinking about accepting or rejecting that offer, so we had in each scenario, they can accept or reject, reject, accept, accept, reject. Okay. So if they accept this offer, it was like here, person one gets 98, person two gets 2, 99, 1, 100, and 1. So instead of this as being like 0 zeros for the rejected, like nobody gets anything if they reject it, if when I'm offered a really low amount of money, when I reject it, the other person getting 0, because I know they have the control, I know that I was like felt so done wrong, right? Or I feel like they were taking advantage of the situation so much, and then it was so inequitable that by rejecting that offer, I actually get some positive utility that I would pay money to have. Like knowing that they get nothing, the fact that they offered me such a low split, $2 out of that 100, I'm actually I will reject that offer because in rejecting it, that has more value to me than just accepting the $2. Seeing them kind of get what's coming to them, so to speak, right? By offering me such a low amount, I would actually value more than having that $2. Okay. So if I could put a dollar amount to that, I would pay up to $10. Okay? So in all of these scenarios, if you're offering me a very small amount of money, I actually get, and I would call this kind of like spite, right? This is how much I value spiting you, right? That you offer me such a low amount that I want to see you get nothing as well, right? So if we try to solve this kind of using backward induction, what would person two do here? Reject. What would person two do here? Well, 10 is greater than 1, so reject. Here, reject. So now notice person one, if I'm choosing these amounts, I know they're always going to reject. I'm always going to get nothing. Now, this will only be the case until I offer them an amount of money, and I'll skip some values here. But what would have to be true? It would have to be that the money offered, in order for that person to accept the offer, would have to be greater than the value of however much they value kind of spiting this person, kind of giving them this low amount. So let's assume if I'm thinking about the decision between 11 and then 10, right? And then person 2 can accept or reject, accept, reject. So reject, they still kind of get this value of spite here. They accept, they're getting what? 90-10 split. Here, this would be 89-11. Rejecting. Now, you're still offering me low amounts, so I still have some value of kind of spiting you because you've offered me this low amount. But now notice, once I get to these higher valuations, what will person 2 do here? Well, they'd be indifferent, so I don't really know. Here, I know they'll start to accept the offer. So if I'm person 1, I know you're always going to reject if I offer you something less than 10, and I get payoffs of 0. You're indifferent if I offer you 10. So yes, sometimes I'll get 10, sometimes I'll get, sometimes I'll get 90, sometimes I'll get 0. So the expected value there is like 45. But if I offer you 11, I always know you'll now be willing to accept. 89 is higher than kind of that 45. So we'd see that they'll offer that person the lowest amount possible, but that would still be above how much that other person values kind of spiting them for not giving them like an even split of the money. So when we look at the labs, if people offer like really low amounts, I forget the exact value that they found, but it is something like between 10 and 20 if memory serves, where yeah, it's a low amount, but people are still like having $10 in my pocket. I don't value the spite, I know the other person kind of offered me an unequitable amount, but I'm okay accepting it once it gets to like $10. But when you look at these other values offered, like 1, 2, 3, we often see that the other person would actually end up rejecting. So even though if we were just purely, if all that mattered was money, we see that they should be willing to accept that $1 offer. If you value other things, right, those get factored into your payoffs when you're making kind of or solving these games or making these decisions. Okay. All right. Any questions on this? So an example, like these low offers are often rejected, even though if all they cared about was money, the theory predicts they should accept the lowest possible offer of 1. So maybe it's more than just money. And of course, right, people factor in utility, right, to their decision making. Okay. All right. That in mind, got one more question we wanted to work through on this participation quiz. And we'll start to think about this as probably a normal game. So let's say, and it's kind of an interesting example, but let's say I had this thing, and like, let's say I had everybody guess. And if you guess on this problem, any number between 0 and 100, you're going to get full credit for. But let's say you were trying to guess half of the number that was the average of what the entire class guessed of a number between 0 and 100. So this in economics, we start to kind of call like level K type thinkers, right? And so we'll kind of talk a little bit about that, even though I won't push you that far in an exam or a quiz. But we can kind of think about how we could model this as like our normal form game and understand why you should make the certain decision you should in this type of a game. So if you're trying to guess half of the class average's guess, well, if people just guessed randomly, what would the average be? 50? In which case, to win, you need to guess half of that, so you should be guessing 25. Okay. So maybe initially you're like, okay, if everybody guesses these random numbers, and we can kind of model this as person 1 and 2, or you can think of this as like the rest of the class, and then you, person 1. So if we both guessed 25, right? Kind of think about this scenario. If everybody guesses 25, thinking that the average is going to be 50, well, if everyone guesses 25, what is the actual average? 25? In which case, half the average would be 12.5. So in this scenario, nobody would win. Now, if everybody else guesses 25 and I guess 12.5, well, now that is half of, or closer to half of the class average, right? So here, if I'm the only person, everyone else in the class guesses 25, and I guess 12 and a half, I'm going to be closer to what the actual half of the class average is going to be. Okay. So in this scenario, person 1 would win, the rest of the class loses. And then if I guess 25 and the other person guesses instead 12.5, and actually, sorry, this isn't 0. If they lose, -1. And then here, if I guess 25, I lose, someone else or the rest of the class wins. And then if we both guess 12.5, now we're kind of back down to this point where if everyone's guessing 12.5, now the actual average is what, 6.25? So now neither of us wins again. So if I solve this game, what's the best response from person one? If everybody else in the class guesses 25, well, then I should actually guess half of that average, which is 12.5, and then I would win. If everybody else guesses 12.5, well, if I guess 25, I definitely lose. If I guess what everyone else is, nobody wins the game, so that's better. So we kind of have this dominant strategy equilibrium. And then what would person two do? If person one guesses 25, 1 is greater than 0, 0 is greater than -1. Notice we end up with this Nash equilibrium, which we both guess the lower value. Now, these aren't the only two numbers we can guess from. So what kind of then ends up happening here? Well, if I know this is the class average, what do I actually want to guess? 6.25, in which case I would kind of extend this, right? Both of us could guess 6.25. Now, if someone guesses 6.25, half the average, that would actually be correct, right? So now, like here, you can think about the payoffs as I win, everyone else loses. You would have like a much more complicated game, but the same logic would apply, that the incentives are going to be pushing each individual to guessing a lower value, to where the actual long run to the equilibrium would be we should all guess 0. Right? So level 1 type thinkers, we would kind of think about as, oh yeah, we think of 0 to 100, the average would be 50, half that average should be 25. That's my guess. A level 2 type thinker would say, okay, yeah, if everyone's just guessing randomly, the average would be 50, so half the average is 25. But if everybody knows that, everyone's going to guess 25. Half of that average is actually 12.5. So that's what I should guess. But if everybody knows that, a level K type thinker would say, well, then if everybody guesses this, half of what everyone guesses will now be, and kind of so on all the way down to where like a level infinite type thinker would actually say the optimal guess would be if everybody is acting rationally, we should all be guessing 0. Okay? So in this kind of what should that equilibrium be? It should be 0 if we follow that logic. Okay? Now, what do we see play out in practice? Well, not everybody is a level infinite type thinker. Some people only are level 1 type thinkers, right? So they go, oh, the average, of 0 to 100 is 50, half that is 25. A lot of people will guess 25, which means that the average isn't going to be 0. Now, if everybody was acting rationally and was looking at these payoffs and thinking about the game correctly, yes, the equilibrium should be 0. So in practice, with a lot of this more simple, the kind of simple game theoretical models we've looked at, what do I want to call this? Individual irrationality or suboptimal decision making can actually cause what we see out there in the real world to not match up with what the theory would predict. The theory would predict that if everybody is acting rationally and analyzing the game correctly, everybody should end up guessing 0. But we know that in practice, not everybody will kind of think about this correctly. And I think if I remember right, like people generally, this ends up being like most people are like level 2 or 3 type thinkers. So like a lot of people will guess 12 and a half. A lot of people will guess 6.25. Not as many people will actually guess 0. Okay? And even if you guess 0, you won't technically be right because you haven't factored in that not everybody else is going to be acting rationally. So it becomes complicated. Game theory is very interesting, but it becomes very complicated the further you get into it. I always like to kind of go through towards the end some of these more complicated examples that I wouldn't give you or kind of push you that far in the exam or quiz. Really on the exam and quiz, it's just knowing how to solve these simultaneous move models, these decision trees, and then also like 2x2 matrices. So, anything that we kind of have in the slides here would be fair game. But I wouldn't even push you to a 3 decision normal form game matrix. I would keep it at 2. Okay. But I think these are kind of interesting examples that you can kind of see how this plays out, not just like with firms, but individual decision making. So game theory is very interesting in understanding markets. It's also very interesting in understanding consumer or individual decision making as well. Okay. All right. Any questions for me? So we got the participants once again. Any number here. If you haven't already guessed, I would try to actually guess what the class average is. I'll try to look at it and discuss what it is tomorrow, just out of interest. So even though if I've explained it to you, probably should have held off on this and seen, got you to actually guess. My other section, I remember to say that. So I'll kind of tell you what the results were from them, to where I told them to guess a number before we actually went through the logic that technically the answer should be 0, although we know not everybody will kind of be acting rationally, and we probably will see something slightly above 0. So I'll kind of look at that data from my other section and kind of bring it in tomorrow just to kind of see how it actually plays out. Okay. All right. And this section's a little smaller, so the other one will be more representative because like 1 or 2 people being off here will like greatly skew the results. So it'll be more interesting to kind of look at that. All right. So got that participation quiz in. I'll publish that module 12 quiz, right? That'll be due at the end of the day, Thursday. And for the remainder of class, that module 13 reading is due before we start tomorrow. But I just want to introduce the topic of what we're going to be looking at tomorrow. So we've talked about perfectly competitive markets, and we've talked about monopolies, right? So what we're going to talk about the next 2 days will be monopolistically competitive markets. So with perfectly competitive markets, we said many firms, identical products, right? Many buyers, nobody has influence over the price. Monopolies, we had one firm, complete control over the price. The in-between, so game theory was helping us to think about, okay, what if there's 2 firms? What if a firm's thinking about entering or exiting? So there we're really thinking about like a small number of firms, or what we call oligopolies. Okay. Now, what we'll focus more on the next 2 days will be these monopolistically competitive markets, which is where we still have many buyers and sellers of a product, right? But we're going to have slightly differentiated products. Okay, so we're going to have many buyers, many sellers, but they won't have the exact same product. Okay, so this is the idea. Like I think I give some examples here, like fast food. So I think about like Chipotle and Qdoba. They're really in the same market, right? They're 2 firms in the same market. They don't have complete control over the price of a burrito because their burritos are slightly different, right? And so they've differentiated their product a little bit so they have some market power, but not like complete market power like a monopolist would. Now, we're also going to require free entry and exit, just like we had for perfectly competitive markets. But this product differentiation gave them some monopoly power. So monopolistic competition, it's kind of like a mashup of both monopolies and perfectly competitive markets. So just like perfectly competitive markets, many sellers, free entry and exit. However, it looks more like a monopoly because they have a very unique product. There's no close substitutes. Monopolistically competitive, they have slightly different products than everybody else. So they're going to have like some substitutes, but they're not perfect substitutes, right? Like they were for perfectly competitive markets. So it's kind of a mashup of the two. And what we'll end up seeing is a lot of the results of this market, in some ways, it looks like a perfectly competitive market, and in other ways, it looks more like a monopolist. Okay. Excuse me. So we'll kind of go through, analyze these firms' decision-making tomorrow and on Wednesday. We'll see that they look in some ways like a perfectly competitive market, other ways like a monopolist. We'll kind of talk about what those different ways are. But other than that, I think that should kind of do it for us today. We'll kind of wrap up there. I don't want to get too far into this without, everyone I know will have went through that module reading by tomorrow, or at least you should have. And then we'll kind of work through all this monopolistic competition stuff. That will really take us, that was the last thing we cover. I think, we won't get through all of it tomorrow probably, but we'll get through a large majority. So Wednesday, I would expect us to finish module 13 and likely have a little bit of time to start going through some of these practice problems. Okay. So the last exam, all that's going to be on there is modules 10, 11, 12, and 13. So, we're reusing some of the stuff we talked about before, right? We like back in perfectly competitive markets, we were drawing demand shifts. We were thinking about supply shifts possibly, but really the only types of questions you'll see are the types of questions that you were seeing on the module 10, 11, 12, and 13 quizzes. or the module 10, 11, 12, and 13 kind of material. Okay. Practice problems would be another good thing to look at. I have module 13's stuff up there. So if you want to start looking at those practice problems, using those to start studying for the final, as well as we start to cover this material, that would be a good place to start since you don't yet have that module 13 quiz. Other than that, are there any questions for me before we kind of end, the recording here today? All right.